So here we are inside the topic of linear regression, and related topic, I would say, is also correlation, especially correlation computed by Pearson's formula. So before we start, it's good to define some basic terms, and I know that for most of you, it will be once again a recap, but maybe that you didn't previously pass the course in English, so you would also recognize English expressions. So if we are discussing about relationships for two variables only, and if I would define property for these variables, so mainly we would be discussing about cardinal variables, or if you take into account terminology in Spss, JAMOVI, or JASP, so it could be described as a scale. So for two scales or two cardinal variables, or long scales, in other words, if we try to find relationship, we would apply so-called simple regression. So simple regression means there is one variable, and I would like to somehow prepare a model for the relationship. If you have more than two variables in one statistical model that is based on regression, we are usually discussing about multiple regression. So simple and multiple regression, the difference is only if you have two variables at once or more variables at once. And you know also from previous statistical courses a little bit about the difference between dependent or independent variable, or sometimes we also use a discussion about outcome and predictor. And the third pair can be found in the literature as explained and explanatory variable. So if you can imagine a real example, and we will be computing such example in a few minutes, so we will be discussing about prices of flats and about sizes of flats. My question is simple and straightforward. What is dependent variable and what is independent variable, price and size?
Price would be dependent.
Price would be dependent and size would be independent. As usually, price depends on the size, yeah? So that's quite easy. I will give you one more example, and let's try to think about this example that sometimes it can be a little bit tricky. If we would take into account classical example from economic sociology, and we would be discussing about relationship between income and education. What would be dependent and independent variable?
Income is dependent.
Income is dependent and education would be independent. But this is valid statement only in the case if I am discussing about my income in some current job and my previous education. Let's imagine I would be, for example, discussing about some advanced education during my career and about my income. Then maybe my current income could be predictor of my further education in my advanced career. As well as another example, I would say near analogy to this, I can take income as the predictor of education of my children. So it really matters that I would think about substantive reasoning behind my model, and I must substantively decide which variable is dependent or independent. Maybe I would add last one comment to this topic. It means differentiation between dependent and independent variables. From statistical point of view, there is no necessity to differentiate. If you prepare the model of my income versus my education, and income would be dependent and education independent, and reverse model, these models would be from statistical point of view the same. So it means they would have the same, for example, explained variance and many other properties. So statistics or statistical software cannot distinguish which variable should be dependent and independent. So it is always your decision. So you, an analyst, must decide which variable is dependent and independent. And I would like also to add, if you are discussing about these dependence and independence, that for linear regression, we would treat dependent variable classically scales or cardinal variables. Then we would switch into the logistic regression. And for logistic regression, our dependent variable will be, for the easiest case, binary. So it means it would consist only of two values, or it can have more than two values that are not ordered. So it means it will be multiple nominal variable. That's why we usually call this logistic regression as multinomial logistic regression. And we can also apply a similar model to variable with more than two options that are ordered. So it is ordinal variable. So we can also discuss about ordinal logistic regression. So based on different scaling of dependent variable, we can distinguish different models. Linear regression, binary logistic, multinomial logistic, sometimes it is also called polytomous logistic, and ordinal logistic model. So that's the first intro. We will discuss also about dependent and independent variable during the discussion about structural equation models in this course. And we wouldn't discuss about dependent and independent variable mostly during the discussion about latent class analysis. So there are some statistical models in which we do not differentiate between dependent and independent variable. One last comment, and I hope it wouldn't be a big surprise during the course, that we will briefly switch from discussion of dependent and independent variable during the discussion about structural equation models into, I would say, analogy, which is usually discussed as endogenous and exogenous variables. So instead of independent and dependent, you will be discussing about exogenous and endogenous variables, and it will be near the same discussion. I will give you more reasons why we would be switching into this different style of terms later. So once again, go back. Currently, we are discussing linear regression, and our dependent variable must be cardinal or at least long scale. It is well known from data simulations that also for longer scales that are ordinal, and at least they have 10 points, you can also apply linear regression model. But once again, this is not result of some statistical proof. It is result from some data simulations. And independent variable or variables, if you have more than one, we discuss about multiple regression as we discussed previously. So independent variables are mostly, once again, cardinal, long scales, or at least long ordinal scales. But we can also apply, and those of you who passed a bachelor course here at the faculty know that you can also apply binary variables. And by some magic, I would say, we can also apply nominal or ordinal variables as so-called dummy variables. We will discuss about these options later. So once again, dependent variable for us would be cardinal, independent cardinal, or binary, or we can somehow prepare a set of binary variables that are called dummy variables. So that's basic introduction into terms that are necessary to know. And we are discussing about linear regression model or about regression models as a whole. The main goal of regression task is to explain dependent variable. So that's why we sometimes call this variable as explained variable. And those that are present in my model for explanation, they are called explanatory, as they are helping us to explain. So we try to explain changes in dependent variable by changes in independent variable or variables. And if you are discussing about linear model, there is one more assumption that is necessary to hold. So it means we need at least 2 variables, at least one should be cardinal. And if I would like to apply linear model, it should be following my data that relationship between dependent and independent variable is linear. So it means if I have only 2 variables, it can be graphically described by the line. So if line can describe my relationship, maybe that linear regression is good model for my data. If the relationship is far from linear, so linear regression wouldn't be the best choice. And maybe I would need some special model. And if I apply regression into my data, so my final result would be usually some equation. And for equation, I will have some coefficients and their evaluation, etc. We will be discussing later. So I would try to find this equation and to interpret these results and all the properties behind. As we are currently following advanced course, I will not go only into analytical details, so we will not be only computing and interpreting results, but I will also show you some parts behind the scene. So it means we will go also into some statistical details that are behind. So let's start with the simplest model. So let's imagine we have only one variable which is dependent and one variable which is independent. For the simplicity, let's imagine the case prices and sizes of flats, income and education measured in years, etc. So we have only 2 variables, and here we are. So for simplicity, we would have 1 cardinal variable as dependent and 1 cardinal variable as independent. And we know from, for example, previous research that the relationship is linear or close to linear. And we will try to perform some computation in JAMOVI. And before we start computations, it would be good to check data. It should be first step every time. And the second step is, before computation, it would be good to see the picture of my data. So it means to prepare the chart. Currently, we are discussing about relationship for 2 variables. We usually call this chart XY chart or dot plot. So we would ask, of course, JAMOVI for preparation such plot. And we can at least graphically evaluate whether my picture seems as real relationship or not. And the picture is also advantageous, according to my opinion, that I can also find some extreme points in my data. So maybe I would be also able to detect some strange points that could maybe strongly or quite strongly change the computation itself. So this is also the advantage to prepare the chart before any computation. So I would like to ask you if you can open JAMOVI, and we would open data flats SAV in JAMOVI. And then the first step would be checking of data graphically and analytically. So if you like to open data, once again, here on the left upper corner, there is an icon with 3 lines. Here, if you click, you can find open. And here you can find the folder in which you saved the data. So I must find this course and file flats SAV. And I guess that in a few seconds, this is quite small data file. You would find data file, which is starting with the variable price and size. Both of these are defined as cardinal or scales. Then there is a definition whether the flat is new or not, the size of the balcony, reconstruction, city size, and then some additional variables. I hope it works on your computers. So here we have a data set. I can mention, as I promised, to use this data without any additional information. So I can only say that these are approximately 10 years data real data from Czech market, from one Czech district only. And if you can see the prices, so you can see that situation 10 years ago was totally different from current situation. Then later we will check descriptive statistic. You can also find that for the first case, there is a missing value for size to see that also missing values can be present. And of course, these cases will not be including into data analysis. So size is missing for the first case. And before we start to compute our regressional results, my proposal is to check at least descriptive statistics for price and size. So the easiest way is to go into exploration. So the left menu, here we can go into descriptives. And here you can take price and size, and you can see that by default, you would get descriptive statistics such as number of units, mean, median, standard deviation, minimum, maximum. If you are able to work with SPSS, so you know that this procedure is called descriptives in SPSS. So I will take price and size. And here you can see very simple information that number of valid values 263 for price, and for size, one value is missing, as we have checked previously. So here it is, one is missing. Here we have the average price of our flats, nearly 1 million crowns, and average size of flats, approximately 66 square meters. Here you can see also median, so slightly less than 800,000 Czech crowns, and 62 is for size, standard deviation, minimum, and maximum. At least if you check these values for minimum and maximum, you can see very strange maximum for sizes. Once again, the file is about flats, and the biggest flat in my data file is big as 403.9 meters. That's very, very big flat. I remember that the first time I checked this data, so I was totally surprised, and I said, no, it's impossible. So that's why I asked the client who provided data, and they said, yes, that's the flat, only flat which is combined of approximately 10 flats previously. So this is flat, but as you will recognize in a few minutes, at least by Graphically inside, maybe that this flat would totally change our results. We can, for example, check the mean here, 66 square meters. And I guess that if we exclude only this extraordinary big flat, the mean would be quite different. I guess it would be approximately 54, something like this. So that's very easy impact on descriptive statistics, but not only impact on descriptive statistics, but I guess that this big flat would also influence a lot correlation or regression relationship between these two variables. So that's why we will maybe decide to exclude this flat from next computations. But currently, here it is included, and I would go into graphical style of reasoning. So I would ask for regression currently, and I would ask for correlation matrix. So correlation matrix in SPSS would be called as part correlations. So it means correlation for two variables only. If you would like to compute partial correlation, here it is by special dialog partial correlation. So correlation matrix, and you can see very easily by this dialog that only cardinal variables can be included or ordinal variables. That's correct, as correlation coefficient, at least by Pearson formula, which is default, is designed for cardinal variables, and Spearman and Kendall-Stowe are designed for ordinal. So for nominal variables, you cannot apply this procedure. In JASP or JAMOVI, usually all procedures follow this logic, so there is predefined level for variables for every procedure. If you would like to compute the procedure for another variable, of course, it is still possible to go into data and change scale for the variable. That's the option. So I would take price and size. And we can see by default that SPSS computed for us the correlation coefficient. So this is first substantive result. And we can recognize that for data. So it means, if I remember well, these are 262 cases currently. So the computed correlation is 0.649. It is, according to my opinion, extraordinary big correlation. If you compare this result to all your previously computed results for correlation, I'm sure that this is very big value. So welcome in the sphere of economics, where big correlations can happen very easily. This is not, I would say, weak social sciences, sociology, social anthropology, political science, etc. So 0.649. And maybe we will recognize in a few minutes that this value is still biased. So it means it's not correct if we would exclude some extreme points, such as big flat with more than 400 square meters. So maybe we can also find even bigger value for correlation for these two variables. So that's it. Here, if we discuss about these outputs, we can see also p-value. So maybe we should repeat briefly which test is currently performed by JAMOVI. So here we have the correlation for my sample, which is 0.649. And my question is, okay, this is the correlation for this small sample of slightly more than 200 flats. But can I find also relationship for price and size for all population of flats in the Czech Republic from which these were selected? That's the question behind the scene. I would add maybe, I would say, slightly implied answer. Maybe that this question is totally silly. If I can see correlations such as 0.649, and I am trying to correlate price and size, I am not expected that these two phenomena are not related at all. So the question whether they are totally independent is quite silly question, according to my opinion. So not all statistical tests are useful, I would say. But as we would like also to learn something from statistics or prefer recap, I would add that classical test for correlation, which is here presented by p-value, is following. Null hypothesis is saying there is no relationship at all for all flats in the Czech Republic, etc. An alternative is saying, yeah, there can be some relationship, positive or negative, as we are currently applying so-called two-sided testing. Okay, p-value is very low. You can see, I would say, quite nice format, which is applied in JAMOVI and JASP. It is also applied in the last two versions of SPSS. So instead of typing 0.000, which was previous format in many statistical packages, currently this is maybe better format. It is lower than 0.001. 0.000 is nothing, once again, it's total rubbish. So that's why packages converted in last years into this, I would say, better format. So here you can see that p-value is quite low one. So if I correctly try to evaluate the hypothesis, so first of all, I would say, okay, my probability getting of my data, it means with correlation of 0.649, or even bigger or lower than minus 0.649 is very, very low if these two phenomena, prices and sizes, would be totally independent phenomena. So according to classical decision, I would set up alpha, for example, 5% at the beginning. I would compare p-value and alpha, and I would reject null hypothesis. And I would say, okay, it seems that prices and sizes are somehow related. Once again, that's not big rocket science. That's total rubbish, I would say. As if I can see correlation 0.649, I don't need test at all. So that's first insight. So that's about correlation. If you like, and in JAMOVI and JASP, you can find it in many, many last versions. You can also ask for confidence interval. So I would ask for confidence interval here in these additional options on the right side. You can see that by default, 95% is included. And that's why we have two new figures in the table. So it means that it seems that correlation can be as high as 0.71 or as low as 0.57. So that's rough estimate, I would say, of correlation for the whole population by confidence interval. If we discuss about p-values and their misconceptions and their misinterpretations, we could perform the same task also for confidence interval, but we would skip such discussion. So we would discuss about confidence interval as a rough estimate of the population for simplicity to avoid some misinterpretations. So that's confidence interval. So at least we have rough estimate that correlation is not zero, is quite far from zero, and the correlation is from substantive point of view big. If we try to evaluate, but once again, it's a little bit tricky correlation, we can simply follow recommendations from Cohen book, which was published for the second time in 1988. So this is very, very famous source for the evaluation of correlations and t-values, etc. And Cohen's recommendation was following. Correlations approximately about 0.1 are quite weak one, or Cohen called these as small one. Medium was 0.3 in Cohen style, and 0.5 or bigger was discussed as big correlation. So from this recommendation, we would say, oh, yeah, lucky, that's big correlation. But I would say, be careful every time about the context. We are discussing about correlation for prices and sizes. We are not expecting some small numbers. But if we would discuss, for example, about relationship between pro-environmental attitude and pro-environmental behavior, we are expecting small correlation. So it always depends on different branch of study in which you are in, and also maybe some special branches inside individual branches. So I would say that 0.7 approximately is for prices and sizes quite normal. So if I would take, for example, data for Germany, Austria, I would expect similar value. So that's nothing extraordinary in general if I compare similar results currently. So that's according to my expectation. Okay, so that's correlation computation test confidence intervals, first insights. And you can also check here that here we can change hypothesis style. By default, alternative hypothesis is that both variables are correlated. Once again, this style of testing is called two-sided testing. So we are testing whether correlation is positive or negative. So no direction. Sometimes we call this style also as non-directional testing. If you expect that prices and sizes are correlated positively, that's what I would expect, for example, you can also check the second option. I expect that these two are correlated positively. We wouldn't recognize here the result, but this one-sided testing, and this is a nice direction to go to positively correlated results, would influence the p-value, and this p-value for one-sided testing would be lower than for two-sided. There is very simple relationship. Current p-value is 2 times lower than previous one. But it's impossible for us to see, as we have here, this short format lower than 0.001. But if I change hypothesis, alternative hypothesis, that they could be correlated negatively, that's what I do not expect, I guess that p-value will be quite big one currently. And you can see that p-value is 1. As once again, null hypothesis currently is saying correlation is 0 or positive, and alternative hypothesis is saying no, correlation is negative. So here, there is no conclusion such as reject null hypothesis. I would be fool if I reject null hypothesis that correlation is 0 or positive. So currently here, I'm concluding I will still keep my null hypothesis. Null correlation or positive correlation is possible. That's why I can see here p-value 1, 0, 0, 0. So here, alternative hypothesis is total nonsense, I would conclude. So that's possibility to change non-directional or two-sided test into one-sided or directional test. So here it is. And last option here in this, I would say, small dialogue is that you can ask also for graphical output. So here is in the lower right part of the dialogue, the plot, and you can ask for correlation matrix. And if you ask for correlation matrix, I hope that in a few seconds, you will be able to see the chart. It is prepared as matrix. So here we have blank spaces for 3 more pictures. We will add these pictures in a few seconds. But still, you can see here regression line. So it seems, at least to me, that linear relationship between prices and sizes is quite useful. The only big exception for this linear pattern is this point. You can see only, it's a pity, but Spss and JAMOVI share this problem, I would say, that JAMOVI take the first variable, price, as independent and size as dependent, x-axis and y-axis. If you would like to reverse it, that's very easy. I would take price outside of my model and take it as the second one. So currently, I guess that my picture will be reversed. And you can see very simply that the pattern of my data seems that line should be fitted like here. But you can see that the line is fitted here, and the reason is this point. We would call later this point as so-called influential. So it influences quite a lot my regression line. It goes down this line from, I would say, correct direction. So this point influenced my computation quite a lot. So maybe that I would like to exclude this point from my computation. So we will make this step in a few minutes. And we can see very simply that some linear relationship can be applied to this picture if we at least exclude this point. Of course, that maybe more points should be excluded, but we won't go into details. We will later, I mean, next time, discuss how automatically, so it means without picture, can detect some influential. So we will learn there are some special computation tools that can help us to find some extra points in my data file. So that's about correlation procedure. And once again, before you start to compute results, every time, please try to check such charts. And last part of this dialogue, so I would go down to this dialogue, can help us to add some more pictures into these blank spaces. So you can ask for distribution, or statistically it is called densities, for individual variables. So you will add 2 more charts for sizes and prices. So you can check, for example, whether these pictures are quite close to normal distribution or not. And you can also ask for statistics. So it means this upper right corner will be fulfilled by some computation. So here we have correlation, and here we have 3 stars notation. So if you like stars related to statistical results, you can see it here. And if you like to see stars in the output here for correlation matrix, you can also click here for additional options, flag significant correlations, and 3 stars are just close to 0.349. And you can see the note under the table that 1 star means that p-value is below 0.05, 2, 0.01, and 3 stars below 0.001. So I must say that statisticians usually hate these stars, so please try to avoid this. But I would like to add one more technical comment. If you would like to have, for example, more decimal places, lower number of decimal places, or make some changes in the output, so you can go to the right upper corner to these 3 dots. And here we have some options how we can change results, how we can change plots, how we can change importing of data, etc. And you can also ask for developer mode of JAMOVI here. So these are some options. So that's JAMOVI and these options. And last step we would perform, as we know, there is some strange point, which is a big flat. So we would try to avoid this big flat from my data. There are 2 options in JAMOVI. First one option, and I guess that you are familiar with this option from a Spss environment, is that you would define missing value for sizes. And it seems to me that if you would take flats 200 square meters and bigger as missing values, so we would exclude this big flat. It would be one option. If you would like to perform such procedure, you would go into data, variables, and you would find description for sizes and define missing values. I would show you another step, which is maybe better, at least for this occasion. And if you go into data matrix, you can, in JASP and JAMOVI and SPSS, it is also possible by selecting data, so you can apply filters here. So if you click into filters, you can type some condition which will be satisfied, and this case would be included into computation, and if condition would be will not be satisfied, then the case will not be included into my data analysis. So for my case, I guess that I should type that size should be below 200 square meters, and then one biggest flat will be omitted from my computation, I guess so. So if I click here to plus, I can add more conditions, as you can see. And I will try to type the condition. So once again, be careful that JAMOVI as well as JASP are case sensitive in comparison with SPSS. So I would type size is lower than 200 square meters. And I guess that if I apply this condition, it is enough to click on enter. So 2 cases will be omitted. One with size, which is missing, and one is somewhere lower, I guess. I will try to find this flat. You can see that filter variable is here on the left side. And if I go down, I can try to find the flat, which is extra big one. Yeah, here it is. This is case 155. It is also omitted, as you can imagine here. And once again, the advantage, or maybe sometimes it is also disadvantage, of JASP and JAMOVI is that every time you somehow redefine data, such as change ordering of categories, make filters, define missing values, all previously computed results are recomputed. So currently, you can see that my picture is changed currently. So big flat is outside from correlation picture, big flat is outside from computation of correlation, and big flat is also excluded from these descriptives. So currently we have 261 flats only. And the biggest flat currently is 179 square meters. So all results are computed. And if you remember well, previous correlation, I guess that current correlation is slightly higher. What was previous value? Do you remember or not?
649.
649. Okay, so currently it is nearly 0.7. So it's slightly increased. And if you check the picture for my data, it seems okay. Currently, linear relationship is much better than previously. And at least for the first insight, there is no big influential. So it seems correct to apply linear regression into this data. So, yeah.
There's some point where we can find how many values we excluded by the filter?
I guess not, at least as far as I know, JASP or JAMOVI, there is no such option as automatically here valid values are all values. Okay. So, of course, the easiest way is to go down through the matrix. I can see here 263, 261, so I know that 2 are excluded. Right. But I guess there is no output which is related to this filtering. Sorry for that. I'm not programming just for JAMOVI. Still, if you would like to cancel the filter, you would click and you cancel the condition. So that's very easy. The only difference between JASP and JAMOVI is that JAMOVI is adding this additional variable filter. In JASP, you are not able to see anything. Only for JASP, there is some special gray color for excluded rows. So that's only the difference for filtering. So that's filtering for my data. And currently, I guess that we are prepared to discuss about linear regression, and we are prepared to compute final results for this first insight into linear regression. So at least graphically, and that's what I would like to start to discuss, we expect something what could be called as positive relationship. So it means the bigger the size, the bigger the price. And the question is only, what would be the average price per 1 square meter? It would be our main results from our computation today for this simple regression case. So that's it. And before we start to compute, I would give some description. So first of all, we will briefly discuss about the logic of computation of regression line, or later for next time for multiple regression about so-called regression plane or overplane. So if we have 3-dimensional space, we are discussing about plane, and if we have 4 or more dimensions, we are discussing about overplane. In Czech v rovině máme přímku, ve 3-dimenzionálním prostoru máme rovinu regresní a ve více rozměrných říkáme tomu nadrovina nebo nadplocha. Okay, let's go back into English. So we will try to fit the best line. We will try also to compute some results, so it means some numbers. We will try also to evaluate the quality of our model. So there are some criteria that will help us to say, okay, that's quite nice model, that's quite poor model. And of course, we will discuss, at least later, that we can somehow improve my model. So it means to add some more independent variables that will be better explaining differences for individual prices of flats. So here we have copied picture from Andy Field textbook. So here is some simple regression case, independent variable as advertising budget in thousands of pounds, and on vertical axis you can find record sales in thousands. And here you can see also not only a regression line and original points, but also so-called R-square. And R-square is nothing more for simple regression than only second power of correlation coefficient. So if I go back to my case and I would compute R-square, so it means second power of Pearson's correlation for prices and sizes. So if it is approximately 0.7, so square would be 0.49. So explanation of prices is approximately in percentages 50% by sizes of lights. So that's quite nice result for our data. Here you can see for field data about recordings, it is 0.335, so it is slightly lower. And here we have a picture that can help us, I hope so, to understand what is, I would say, behind the scene. So it means JAMOVI, JAS, or SPSS, or another statistical packages will compute results for us. So here we have these black points, real combinations of horizontal and vertical variable or independent and dependent variable. So here we have, for simplicity, 4 points. My strong recommendation is, please never apply regression to only 4 cases. Here it is only for simplification and for possibility to use pictures. So 4 points are not enough. But here we have real 4 points. And here we have also black line, which is the best regression line for this data based on the technique which is called ordinary least squares, or in shortage, and you can find it very often in the literature as OLS. So if you find I applied OLS, it means that he or she applied linear regression based on ordinary least square, the most common technique. Usually it is the default for regression computations. And how these OLS are computed. So let's imagine that I would take the distance from this black point to this red point. So this vertical distance, and this vertical distance is called residual. Residual every time in statistics is the difference between real value and between the value that is computed by my model. So here my model is regression line, and estimation for this case of dependent variable is this size of this red point. Real value is this size, vertical size for this black point, and the difference, so it means mistake in my model, is called residual. And I would take square from the residual, and make square means graphically to make this yellow square. And I would take this trick for all 4 points present in my data. So I have small square here, the biggest one, and the second biggest one here. So I have 4 squares, and I try to fit this line in this manner that I would like to minimize the sum of these squares. That's why it is called ordinary least square techniques. I try to sum shapes of all these squares and to minimize this shape. And this line, I hope so, is fitted as this size of these all squares is the minimum. I can inform you very easily that, of course, SPSS or JAMOVI or JAS or R or another packages are not trying to implement all possible lines and are not making these pictures. It would be nearly impossible, as there is indefinite number of these lines. but it is computed by so-called derivations. But still, this is the logic behind ordinary least squares. So we try to find the best line, and this best line is fitted and it fulfills the condition that it has least squares sum of residuals. So that's it. And if I compute these results, so this line can be described by two parameters. Here is general equation for the line. So it means vertical axis or y or dependent variable can be computed as some, I would say, beginning. This beginning is usually called in statistics as constant or intercept. Constant or intercept. And the meaning, graphical meaning of this B0 can be found here. If you are here on horizontal axis at the value of 0, and you take the value of the intersection of the line and vertical axis, so this is the B0. So it means it is the value of dependent variable if independent variable is 0. I would say that quite often, especially in social sciences, there is no substantive meaning for constants. Let's imagine we would take our case. So we would combine prices and sizes of flights. So what would be substantive meaning of constant for these prices and sizes? It would be price for the flat, which has 0 square meters. Of course, I know that situation on flat market is not very nice, but still flats with 0 square meters are not on the market. Believe me, maybe they will be, but still they are not. So interpretation that this is the price for totally empty flat, or we can call it another way, is nonsense. So in social sciences, mostly there is no space for interpretation of this constant or intercept. The similar case can be applied to income and education measured in years. Constant would be income for those who never attended school. Once again, it's nonsense, mostly for developed societies. So that's why usually we are not able to interpret constants, or we need somehow to transform our data. We will learn next time if we would like to use such interpretation. That's why the most important parameter for regression line, mostly for us, is the second one. Here in the equation, there is plus, as I would add to the beginning something more, and I would add something more. Parameter, which is usually called as slope in English, multiply by the value of horizontal axis or independent variable. So once again, for our case, this B1, the slope, would be very simply price per 1 square meter. So it means if my flat will be 1 square meter bigger, the price would be, I guess, something like 10,000 Czech crowns more expensive. So that's the meaning of the second parameter, which is called usually as slope, usually called as B1 in statistical equations. And the meaning is very simple here. So you would add 1 more unit on horizontal axis. This is this blue line with added 1 unit increase. And here it is, vertical increase of regression line by B1. So once again, the easiest interpretation is if independent variable is increasing by 1 unit, dependent variable is increasing by B1 or slope units. That's the meaning of the slope. So 2 parameters, beginning, intercept or constant, and slope. And slope can be positive if the relation is positive. Slope can be as well as negative if the line would go down. And it can happen also that there is no linear relationship at all. So it means that the line would be parallel to horizontal axis, so not increasing, not decreasing. Then the slope would be 0. So these are 3 possible options. And its total analogical correlation coefficient. Positive correlation coefficient means there would be positive slope. Negative correlation coefficient means negative slope or decreasing line. And non-decreasing, non-increasing line, so it means 0 slope, it would be the same as 0 correlation coefficient. So these 2 phenomena are related. Okay, so that's about ordinary least squares technique and its application to regression. Here we have the description we have just described, so I guess I can skip the slide number 9. And here we will go briefly into JAMOVI, and then I will also recompute the same result also in a Spss environment for you to have an option to compare these 2 packages. So if you would like to compute simple regression results in JAMOVI, so that's very easy. So we can go back into our data matrix. We know that 2 cases are already excluded from the computation. One with size system missing value, and one with extraordinary size of the flat. So we can go into analysis, and we can go into regression. And the third option is called linear regression analysis. As you can find here, other procedures are for logistic regression. So we will discuss these in the next couple of weeks. So currently, let's go into linear regression and let's compute our first results. So here we are, and you can see that by default, and that's a slight difference between JAMOVI and JESP and SPSS. JESP and SPSS has the same settings. For JAMOVI, it is slightly different. In JAMOVI, by default, you can find only 2 output tables. One is for model fit. In SPSS, I guess it is called summary. And one is for coefficients. For SPSS and JESP, you would find also one more table, which is called ANOVA table. In JAMOVI, you can ask for this ANOVA f-test in regression, but it will be merged into this first table. I will show you this in a few minutes. But before we start discuss about details, we would perform the basic settings. So we would like to compute linear regression. Prices should be dependent variable. That's why I would define price as dependent variable. And sizes would be independent variable. And you can find it JAMOVI, and the same style can be found also in JESP, is differentiating independence into 2 types. One is called as covariates, and it is expected that these are cardinal variables. And if your variable is nominal or ordinal, but you must set up the scale as nominal, you can define it as factor. The advantage is that JESP as well as JAMOVI, in comparison to SPSS, are preparing so-called dummy variables for these nominal or ordinal variables automatically. So it's not necessary for you to prepare these variables by data transformations. But we have here only one independent variable, which is cardinal. It is called covariate. These terms, such as covariates and factors, is also applied in some procedures of SPSS. So we can move size. And if you move these 2 variables, you would find first table, which is, I would say, recap for previous pictures. As we know that R, or correlation between price and size, is 0.685. We can go back into this picture, or we can go back to correlation matrix, and here it is. We also know that for simple regression, it is enough to take the second power for correlation coefficient and to get R square, or once again, we call this result as explained variance. And Classical interpretation is based on multiplication by 100, and you get the result in percentages. So here, if I multiply by 100 in percentages, I can say that by sizes, I'm able to explain variance in prices by 47%. So nearly 1/2 of the variance of prices is explained by sizes of these flats. I would say substantively, this is quite good result. So from substantive point of view, R² is sometimes called as measurement of substantive significance of quality of regression model. If you would like to add some special name to R², so sometimes it is called as coefficient of determination. And once again, for simple regression, it is nothing more than second power for correlation coefficient computed by Pearson formula. So that's the first result. Okay, here we are. And the second table here is classical table of coefficients. So here we have the value of intercept or constant and the value of the slope. So first of all, I would like to interpret these results. So the meaning of the intercept, once again, it would be quite silly to interpret this value. But if I would like to buy the flat with 0 square meters, somebody would pay me approximately 30,000 Czech crowns, is saying this model. If this would be true, I am really sure that most of people would buy these 0 square meters. But once again, that's totally silly. So we wouldn't interpret this value, that's nonsense. But for the size, the interpretation can be twofold. Classical would be if the size for the flat is 1 square meter higher, you would pay more approximately 40,300 Czech crowns. Or another, and maybe easier interpretation would be that the average price per 1 square meter according to our model is 14,400 Czech crowns. So these are two possible interpretations. And my question, and I would be happy if you can answer, is if you can see these results, so it means especially this estimate for the slope. So is this value valid for the sample of my data or for the whole population of all Czech flats? It is just computed the value 14,289. Valid for sample or for the population?
It is valid for sample.
For sample, thanks a lot. Yeah, so this is the value which is valid for my sample. And as I would like maybe to infer my results from the sample to the population, so I can apply statistical tests for regression and for slopes, as well as for constant or intercepts. We call usually these tests as partial t-tests, as they are applied for individual parameters. And here is t-value. T-value is computed as estimate for my sample divided by standard error. So this value divided by this value is approximately 15. You can compute it alone and check whether JAMOVI is correct. And if you imagine the curve of normal distribution, and you know that -2 and 2 are borders, which are differentiating 5% of extreme low and big values from the rest, 95% of, I would say, quite ordinary values. So 15 is extremely on the right-hand side of the scale of normal distribution. So it seems that p-value, probability of getting of my data, or even more extreme, would be low. And here it is, p-value is lower than 0.001. So this test is discussing null hypothesis, which is saying, if I would take prices and sizes for all Czech flats, there would be no relationship at all. That's null hypothesis. An alternative is saying, there can be some relationship. And here we are saying, oof, there is some relationship as p-value is low one. Once again, we know that p-value is probability of getting my data, or even worse. So it means even more related if null hypothesis is true. So null hypothesis seems it's not true. And we can say, okay, it seems there is some relationship. Once again, nearly silly test in this case, as we know that this relationship is quite strong one. Okay, so that's p-value and testing. That's basic default output in JAMOVI. And we would add some more outputs, and then we will switch briefly into SPSS for comparison. So I would ask for some additional outputs currently. So here you have many options. We would go through these options later. But here, if you like to add some outputs, so we can go into model coefficients. And here you can apply for so-called ANOVA test. And I guess we would get new one result here as additional table. Once again, this third table is usually default in SPSS, in JASP, as well as in R. This is default output for regression. I don't know why is it not default output here. We can also, I guess, get the same result somewhere else. I will try to find it. Here in model fit, there is also F-test output, and it would be added here as the part of the first table. So these are two options how we can ask for ANOVA. Here, one merge table, and here, once again, by omnibus ANOVA test in model coefficient, a separated table, but still the same result. So that's another option. Next option, which is quite useful, as we discussed, every time we would be applying statistical tests, we would be also applying confidence intervals. So here in model coefficients, you can ask for confidence interval as well. And here, model coefficient table would be increased by 2 new columns. So I would ask for confidence intervals. And you can see 2 new columns, 95% confidence interval, lower and upper. So here we can get rough idea about our results. So it means that for my sample, the average price per per 1 square meter is approximately 14,000 Czech crowns. But if you would like to generalize through the whole population, maybe it could be approximately 12.5 up to 16.1 thousand Czech crowns. So these are rough estimates of the slope for the whole Czech flat market. So that's confidence interval. And the next possible output is, but if we have only one independent variable, it's not a very useful output, but we will discuss about this output as well, is to ask for standardized estimate. In SPSS, as well as if I remember well in JASP, it is output which is default. Here we can ask for standardized estimate, and we would get one more last one column, which is here 0.685. My question is whether we didn't find this figure previously. What is the meaning of this figure for simple regression of this standardized coefficient? Yeah, that's the correlation. So if you have simple regression and you compute standardized estimate of the regression coefficient, these two figures are the same. For all more complicated models with more independent variables, that's not true. But here, if you would like to compute correlation, you can also compute standardized estimate for regression coefficient. So that's the option for standardization. If we would have more than one independent variable, the standardized estimates will be useful for possible comparison of effects of individual independent variables. As usually, different independent variables follow different scales. Let's imagine sizes from maybe 20 square meters up to 200. And I can have also another variable, whether the flat is new or not. It would be 0 and 1. So total different scales. So original coefficients, so these estimates cannot be compared directly, but the standardized estimates, they are recomputed into some standardized value, they can be compared. So that's why for comparison of the impact of different independents, we would be using this standardized estimates. So it would be our task for the next time as well. So that's about model coefficients and added values. I can promise we will later also visit another possibilities here, such as assumption checks, model builder, and saving. But for today, if you like to follow our previous steps in JAMOVI, you can save this. So if you click into this left upper icon with 3 lines, so you can click into save, and you can only add name. By default it would be flats. JAMOVI file OMV once again will be saving my data file, all data transformations, all inputs and all outputs into one file. Of course, the disadvantage is that this file is readable only via JAMOVI. It's impossible to open it elsewhere. So I would save it as flats OMD for today. So now it's saved, and we can close JAMOVI for today. And for the rest, approximately 10 minutes, I would open SPSS. So I would open SPSS directly by double-clicking into flats. File. I hope that my license of SPSS still works today. Yeah, it seems correct. And here it is, price and size, and other variables are prepared here. And I would quickly only repeat the procedures we have performed via JAMOVI. So first of all, we know that in JAMOVI we filters out some data. So I will prepare a similar procedure in a few minutes. But before we start, I would check descriptive statistics. So if I would like to check prices and sizes, I would go into Analyze, Descriptive Statistics, and Descriptives. And here I can take price and size together. And by default, only the output is slightly limited in comparison with JAMOVI, but still there is a number of cases that are valid: minimum, maximum, mean, standard deviation. If you would like to add something more, you can go back into descriptives, and through options, you can define more outputs. But I guess it's nearly the same, only you can see that the appearance is slightly different, that rows and columns are transposed here in JAMOVI. Here there were descriptive statistics, and columns were created by prices and sizes. That's the only difference. If you would like to change it here in JAMOVI, there is no such option. You can double click into the table, I guess, and you can by pivoting transpose rows and columns, and here you have the appearance from JAMOVI. So that's the option of changing outputs in SPSS, if you like. And once again, we know that here we have extremely big flat, which was excluded from our previous analysis. So once again, I would decide to exclude this flat. And once again, 2 options are available in SPSS. We can define missing value for sizes, or we can prepare the filtering. I would perform the same operation as for JAMOVI. So I would ask for filtering of my data. So it's necessary to go into data. And here, nearly at the end, we can find select cases. So filtering is SPSS is called select cases. So data select cases. And here we need to define the condition. So we need to select not all cases, as is the first option on the right side of this window, but we need to go into if condition is satisfied. So click into if and 3 dots, and we need to type the condition. So the condition would be that size would be below 200 square meters. Continue, and let's check whether currently we have filtered out unselected cases or delete unselected cases. If you would like to go back to full data file, please check that your output is filter out unselected cases. And currently, if we click into OK, I guess that in SPSS, you can find the case 155 is missing here. That's new appearance in SPSS. Previously, the cases that were excluded were crossed. Here, 155 is virtually missing, as you can see. So this case was excluded from my analysis. If I recompute results, so once again, descriptives, I can see that currently the biggest flat size is 179 square meters. So currently we have the same results as for JAMOVI. Only you can see that previous results are still computed for all units. There's the difference between SPSS and JAMOVI. In JAMOVI, if you change filtering or setting of missing values, all results are recomputed. Here, only new values are computed under filter. And once again, if I cancel the filter, all units will be included into computation. Okay, and correlation and regression in SPSS. So I would go into analyze, correlation. And here you can find, at least in newer versions of SPSS, more procedures. For bivariate correlation, there is not only old version called bivariate, but there is also a new one called bivariate with confidence interval. So I would use the old one. If I take price and size, I can ask for both of these. And it's quite a bit surprised that also in this procedure, you can ask for confidence intervals. So there are two procedures for confidence intervals for correlation in SPSS currently. So I can ask for confidence intervals on simplicity. There are some special adjustments also here. We wouldn't apply these special adjustments for simplicity. So we would use classical Fisher formula for computation. The new at least for last two versions of SPSS, is also possibility to show only the lower triangle of correlation matrix. So it means to hide values that are not necessary to see. So I would recommend you to show this. As the result, you can also hide the diagonal. That's also possible, and click into OK. So here you can see two tables. Here we have correlation, p-value, and number of valid cases. And the second table, slightly recap, once again, correlation, p-value, and also confidence intervals. So that's correlation by SPSS, I would say. And last step we would like to perform is to see a regression analysis, the same regression as previously. So it means correlation, a relationship between prices and sizes. Maybe before computation, once again, chart. So I would go into graphs, chart builder. Here there is a question whether we define properly our scales. So it means whether variables are correctly defined as scale, ordinal, or nominal. So it seems that at least for prices and sizes, that's correct. So click into OK. And here, if you would like choose the same chart as was applied in JAMOVI correlation procedure, we need to go into scatter or dot. Here it is. And it's necessary to move the easiest chart. So it means this left upper corner here to the upper window. And here it is necessary to define x-axis and y-axis. So price on the y-axis and size into x-axis. And we can click into OK. And a few seconds, maybe if your computer is slower, it would be more seconds. You can see the pattern of my data. And if you remember in JAMOVI, also in chess, by default, there was also regression line and also some more computations, if you like. So in SPSS, if you like to add some regression line and computations, you can double click into this chart. And if you double click, there is some option which is in the second row. Here, the icon is called add fit line at a total, nearly at the right corner here. And if you click here, it is asking whether you would like to add mean of y, linear regression, lies, quadratic, cubic function, etc. So linear is default, so I will close it. And here we have regression line, as well as regression equation, as well as R-square 0.47. So currently regression is computed by SPSS in picture. And last step is that we would perform linear regression in SPSS. It means computation procedure. So you need to go into Analyze, Regression, and Linear. Here we are. And here we need to define prices as dependent, sizes as independent. For simplicity, so it means we wouldn't go back into this dialog. I would go into statistics, and I would ask for confidence interval. And I guess that our results currently would be comparable to last results in JAMOVI. As in SPSS, standardized results are default, and also ANOVA table is default output. So click into OK, and here we have 3 tables. So first of all, R-square, and also so-called adjusted R-square. We will mention this phenomenon next time. Here we have the test of the model as a whole, so-called overall F-test or ANOVA table. And here you have coefficients. Only the order of individual columns is slightly different from JAMOVI. For example, standardized coefficients in JAMOVI were the last one. Here we have as the third one, but still unstandardized coefficient, standard error in JAMOVI, it was called only SE, t-value as the ratio between B and standard error, p-value called sig here, and lower and upper bound, it means 95% confidence interval as last 2 columns. And once again, you can see, at least in newer versions of SPSS 27 and 28, the appearance of small p-values is lower than 0.001. So that's new style in SPSS for the appearance of small p-values. I guess there is no necessity to interpret results, as we discussed about substantive interpretation previously. So we know about all these results. So that's only brief repetition of analytical steps in SPSS environment. If you like to see how it works in JASP, I can recommend you recordings from last year where all these procedures are performed in detail in JASP as well. So that's all for today from